Okay, today we're talking about L'Hopital's rule. L'Hopital came up with this rule with limits, and basically what happens is what you want to try to figure out is if we can find the limit of functions a different way. Whenever we did limits, there were lots of rules about trying to find limits. You could factor, you could use the conjugate, you could find common denominators and work it out. There were several different ways. The problem is limits don't always work that easily. There's not always an algebraic way, and so we needed some other process. So L'Hopital's rule applies when we have something called an indeterminate form. Whenever you plug in the value that you're approaching, if you get a form that looks like infinity over infinity or 0 over 0, or any combination of like negative infinity over infinity, these are called indeterminate forms because this does not equal 1, this does not equal 0. These are indeterminate because we don't know what they equal. They could equal many different things depending on the values that you're approaching. And so this rule applies in situations like this. There are more indeterminate forms than just these two, but these are the two that we're dealing with in today's video. So before we go on, there's two other limits that I want to talk about that I think are important to talk about. And here's one of them. The limit as x approaches infinity of 1 over x. If I think about the graph of 1 over x, it looks kind of like that. So as I approach infinity, this graph is approaching the x-axis, so you get 0. That's the horizontal asymptote. Another way to think about it is the bottom is getting bigger and bigger and bigger. The top is staying the same, so that means that the fraction is getting smaller and smaller and smaller. So if you ever have 1 over x, or really any number over x, the limit of that is going to be 0, and that's important. Another one that I want to talk about is the limit as x approaches 0 from the right of 1 over x. This is another one that I just kind of want you to know. And if you look at the graph and I look at the right as I approach 0, as I get closer to 0, that's going up. This is going towards infinity. Another way to think about it is that the x is getting smaller and smaller and smaller. For example, we might have 1/5, and then 1/4, and then 1/3, and then 1/2. And what happens is those numbers are getting bigger because we went from 1/5 to 1/2. And then as we get even more smaller numbers, the numbers will even get bigger and bigger. So this is going to be infinity. When I say that this limit equals infinity, I don't mean 1 over x equals infinity. I'm talking only about the limit. So now let's get to what L'Hopital's rule actually says. So L'Hopital's rule says if you have a limit as x approaches something of f of x over g of x, and when you plug in a, that should be an a right there on g, so when you plug in a, if you get one of these indeterminate forms, if you get infinity over infinity or 0 over 0, or even negative infinity over infinity, then you can use L'Hopital's rule. If you don't get one of these forms, then you've got to do something else. Okay, so L'Hopital's rule only applies if you get these two indeterminate forms. Here's what the rule says. The rule says that the derivative of f and g, if you divide them and find the limit as x approaches that same value, that it would equal the original limit that you're looking for. So as long as you get infinity over infinity or 0 over 0, you can find the derivative of f and the derivative of g and then find the limit, and that will give you the same value as the original question you are being asked. So this is the actual rule, and that's what we're actually looking at as we do a bunch of example problems today. Alright, so as we look at this, the first thing that we're going to do, I want you to know that you could do this the old way, meaning I could factor out the 2 and continue factoring. Canceling, plugging in the number I'm looking for. When I plug in -1 there, That would be negative 2 times 2, and I would get 4. So I can do it the old way. However, I want to show you the new way. The new way applies to even all of the old ways as long as you get infinity over infinity or 0 over 0. So we're going to start by plugging in negative 1 here. If I plug in negative 1 on the bottom, I get 0. If I plug in negative 1 on top, I also get 0. Notice I didn't put an equals there. It doesn't really equal 0 over 0. That's just what I get. That's very important. So what L'Hopital's rule says is that I can find the limit as I approach the same value of each derivative. So the derivative of 2x squared minus 2 is 4x. The derivative of x plus 1 is 1. So this limit and this limit is the same. Plug in negative 1, I get negative 4. And that's what I got up here as well. That should have been a negative. So as long as this is true, the limit's pretty easy as far as the derivative is concerned. So I'm going to do the rest of them this way. Keep in mind you could do them that way if you wanted. Alright, so let's talk about this one. As you approach infinity, what happens? Well, just think about plugging in really big numbers here. The top and the bottom both will give us big numbers, so we have infinity over infinity. Alright, what that means is that when I find the limit here, I'm going to find the limit of the top, or the derivative of the top. I'm going to find the derivative of the bottom. Don't just start plugging in infinity until you've simplified. Here you can simplify, and so you get 3/2. Yes, you would still get infinity over infinity, but, I mean, you can just go ahead and simplify there. Whenever we did limits as x approaches infinity, we looked at top and bottom having the same degree, and that's how we found the limit of that one before. But starting with number 3, this is problems that we were not able to solve originally, and so these are the ones where L'Hopital's rule is really important. So looking at this problem here, when I plug in 0 up there, e to the 0 is 1. So this is 0 over 0, which means I can find the derivative on top and bottom. The derivative of the top would be 2e to the 2x. Derivative of the bottom is just 1. Plug in that 0. E to the 0 is 1. 1 times 2 is 2. Okay. Number 4, plug in 0 first. E to the 0 is 1. 1 minus 1 is 0. Plug in 0. That's 1 minus 1, which is also 0. So the derivative of the top is 2e to the 2x. The derivative of the bottom is e to the x. If I plug in 0 now, I get e to the 0 is 1, so I get 2 on the top. E to the 0 is 1, so 2 over 1, so 2 is my answer. Number 5. The limit as x approaches infinity of natural log of x over x. When I plug in infinity, I get infinity over infinity. That means I can use L'Hopital's rule. And L'Hopital's rule says let's find the derivative of the top, which is 1 over x. The derivative of the bottom is 1, so I can just put divided by 1. Now I'm trying to find the limit as x approaches infinity of 1 over x. Think about plugging that infinity in. That's where we talked about at the beginning that the bottom's getting bigger and bigger and bigger, so the fraction's getting smaller, so that equals 0. Number 6, plug in negative infinity. So the top's going to give me infinity. Negative infinity would give me e to the infinity, so I still get a big number on the bottom. So we're going to continue and we're going to find the derivative. The derivative of the top is 2x. The derivative of the bottom is negative e to the negative x. Okay. Think about plugging in infinity again. So the top still is negative infinity. The bottom, again, is negative infinity. It is possible that you would have to do L'Hopital's rule 2 times or 3 times. So we're going to do L'Hopital's rule again, which means we're going to find the derivative again. The top would be 2. The bottom would be the derivative of the powers of negative, so that would make that a positive. All right, so pretty much we have 2 over, this comes out to be e to a big number, so infinity, 2 over infinity. The bottom's getting bigger and bigger and bigger, so in this limit, the derivative or the limit would be 0. Okay. Number 7. Number 7 is not written as a fraction, but in order to solve this problem, you may want to write it as a fraction to make it a little bit easier. See how this has a negative power? Well, I'm going to bring it to the bottom. And so all I've done is I've rewritten this limit this way. Now think about plugging in infinity again, so infinity over infinity. That means that I can do L'Hopital's rule. The derivative of the top would be 1/2 x to the negative 1/2. The derivative of the bottom would be e to the x. Because you have a negative power on top, at this point I would probably rewrite it and put that negative power on the bottom. And we'll go ahead and make it a square root of x. And then when I do that, the 2 and the square root all go on the bottom. So we've got like an infinity on the bottom. So 1 over infinity, if you want to think of it. The limit comes out to be 0. That's a weird one. Number 8. So the first thing we want to do here is plug in that 0. Sine of 0 is 0. 7 times 0 is 0. That means we can just go ahead and use L'Hopital's rule. The derivative of sine of 10x is 10 cosine of 10x. The derivative of 7x is 7. And now when I plug in 0, cosine of 0 is 1. So we've got 10 over 7. Number 9. So when I think about plugging in infinity here, I do get infinity over infinity. So that means that I can use L'Hopital's rule, which is the derivative of the top and the derivative of the bottom. Plugging in infinity reveals still an infinity over infinity, so I'm going to do it again. So 2 over 5 times 5 is 25, e to the 5x. Plugging in infinity gives me an infinity on the bottom, a number on the top, 2 over infinity. So that limit is going to be 0. Notice I never put equals right here. That's because it really doesn't equal that. That's just what you get when you plug it in. Number 10. So plugging in a 1, natural log of 1 is 0. So we have 5, or 0, not 5. 5 times 0 over 0, meaning I can use L'Hopital's rule. Remember to always check it. There are times it doesn't work. The derivative of the top is 5 over x. The derivative of the bottom is just 1, so I can leave it like that. Plug in your 1, and you get 5. Alright, number 11. If I plug in 0, I do have 0 over natural log of 1, which is also 0. So I can find the derivative. The derivative of the top is 3. The derivative of natural log of something is 1 over x plus 1. If I rewrite that, that would be 3 times x plus 1. At that point, you can plug in 0. You do get 1 times 3, so you would get 3. You could plug it in there. I just like to simplify if you can. Number 12. It is 0 over 0 again. So we're going to find that derivative. 1 over the derivative of tangent is secant squared of x. Remember that secant squared of x is the same as 1 over cosine squared of x. Cosine of 0 is 1, so secant squared will also be 1. So this is 1 over 1, which is 1. I'm going to skip on down to number 15. When you plug in infinity, you do get infinity over infinity here. The derivative of natural log of x to the third is 1 over x to the third times 3x squared. And then the derivative of 2x squared is 4x. We do need to simplify this a little bit. When I simplify there, that would be 3 over x. And then I also want to bring this up. So now we have a problem like 3 over 4x squared. So when I plug in infinity, I have 3 over infinity, which comes out to be 0 for the limit.